If you're new to this channel, you may consider subscribing and hit the bell icon so that you continue to receive the updates. Also, after watching this video, you may want to refer to some of the playlists that we have created for people who are interested in in-depth knowledge. These are the videos in the right sequence, which will give you thorough knowledge of the subject. Please share it with all others who might benefit. Let's get started. So in our previous video, we talked about the special sequences, and in this tutorial, we'll be talking about the applications or the hands-on aspect of it. So let's import the regular expression library. And let's say we are coming up with another string which says cats are lovely pets. In computer vision, cats versus dogs classification is very common. Let's say this is our string and we want to search for specific patterns. So if you remember, special sequences had this backslash uppercase A, which essentially represents the beginning of a string. So if you're looking for a pattern which talks about a string that begins with cats, that's what it'll find out, where exactly this pattern is. Is it there in the beginning of the string or not? In our case, we have this here. We will be able to find a span for this in particular. It says from 0 to 4. So index 0, 1, 2, and 3 essentially capture the word cats. Now, if we do just cats and we remove this backslash A, what does it mean? We're no longer restricting it to the first occurrence or the beginning of the string only. We are looking for the presence of cats as a pattern anywhere in the string. And you can see it's actually used twice, cats here and cats here. So it should talk about both these spans now. Let's run this. So you can see index 0 to 4, essentially not including 4, 0, 1, 2, and 3, and 41 to 45 and not including 45s. This captures the second occurrence of cats here. Let's say we are also looking for the presence of the word dogs here, and this may start with an uppercase or a lowercase. So we put an uppercase D, pipe lowercase d, could be any of these, and we've made a group out of it, and then we are looking for OGS. Now, S followed by a question mark means even if you do not have an S at the end, it will find out. Question mark essentially, if you remember, indicates the presence or absence of whatever precedes it. So S is optional here. So it would identify the word dog, whether it starts with an uppercase or lowercase, and it will also identify dogs because S is something that's optional here. Let's see. So in our string, if you see, we had the word dogs here, and it kind of identified that properly. Index 49 to 53. 53 is not to be counted. Now let's take the second example. We are saying catch the concatenated categories from the scattered catalyst. If this is a made-up sentence, of course, and doesn't have a lot of meaning, but we are trying to look for a pattern called cat here. We'll understand the importance of word boundaries through this. So let me first run this. And now let's see what's the pattern that we're looking for. So we are looking for the pattern called cat, which is in between the word boundaries. This is the beginning of a word boundary, and this here at the end is the end of the word boundary. So it starts with a word boundary, ends with a word boundary is what we are looking for. What do you think it will be able to find? Let's say we run this in. What is the outcome that we get? It doesn't give any output. Why? Because you don't have the word cat occurring here independently. So if we had the word cat here anywhere, it would have found it. We have cat, but it's either in between a string or in the beginning of a string, like for example here. But it's not something which is properly enveloped by the word boundaries, and that's why it didn't return any output. If you, let's say, change this and say that anything which has the word boundary in the beginning, would it be able to find out something? It'll be able to find out words like categories and catalyst. Let's run this. Okay, this is already run. I'll run this again. See, so it found the presence at two places, 23 to 26 and 53 to 56. Let's figure out what are these indices representing. So we go to the text too and take everything from index 23 onwards and index 53 onwards. You'll find out what kind of words have been captured here. So see, categories and catalyst. These are the words which essentially begin with the word boundary and then follow with a sequence. There's no restriction at the end. Let's say we try to make it optional. We say it begins with a word boundary and then starts with a lower or an uppercase C and has 80 after that. What all would it be able to find out? Would it be able to find out the first occurrence of cats? So yes, it is the first word that began with the pattern cat. Last time it was not found because we have an uppercase C here. When we made it an option, it could be a lowercase c or an uppercase C and looked for cat. It's able to find that as well. Now let's say we put another pattern condition here that we only want this occurrence of cat at the beginning. It could be an uppercase or a lowercase c, but we want that to be at the beginning. That's what this \a represents, right? So then it'll only identify one of these, and in fact, the first one, because the other words, categories and catalyst, were not at the beginning of the string. And let's say if we don't put any word boundary, then what happens? So we are saying that we're looking for the pattern called cat. It could be beginning with an uppercase C or a lowercase c. What does it return now? It returns more occurrences. And what are these? It's basically catching the pattern cat all across. It's able to catch the pattern cat everywhere. It catches it here. It catches it for concatenated, categories. Scattered also has a cat, and catalyst. So 1, 2, 3, 4, and 5. 5 occurrences. Now let's interpret another pattern. So we are saying A to Z and 0 or more occurrences. So this asterisk is 0 or more occurrences, right? As a meta character. So it is representing alphabets occurring 0 or more times. Then you have the pattern called cat. And then again, after that, also you may have alphabets 0 or more times. So essentially, this is going to look for such occurrences where cat may be lying in a pattern. And you can see it finds out the specific words for us now. Why? Because if you see concatenated, so this kind of confirms. So CON is a sequence of alphabets repeated one or more times. In this case, you have CON, so 3 times, cat, and then anything that follows repeated multiple times, right? It is also able to catch categories. Why? Because we said 0 or more. So maybe in the beginning of categories, you don't have any other alphabet. After that, you have a pattern. It will be able to find that. Similarly, scattered has an S in the beginning. So 0 or more. So 1 occurrence, which is what? S. And then cat. And then whatever follows, it's able to catch. So it's able to catch all those words which contain the pattern called cat, maybe enveloped or maybe optional. If you had just the word cat, it will also be able to identify, because we've given an option for the characters in the beginning and at the end. So it may or may not be there. It will still be able to identify the pattern cat. Why did it not capture the first word? Because it has an uppercase C. Otherwise, it would have also captured that. Now let's look for the \B, which is essentially representing something that's not a word boundary. Would this give us a similar output that we saw earlier? Let's run this. No, it's giving us a little different output. Why? Because out of these 4 words, if you see, categories began with the word boundary, and catalyst also began with the word boundary. You can look at the index values to understand where this pattern cat appears. 13 to 16. See, it says from 10 to 22. 10, 11, 12, 13. This is where the cat piece begins, right? So that's what it's considering. And what about the second occurrence, 44 to 47? Which range would it fall under? 43 to 52. So again, if you exclude S, it would have started with what? If S was at 43, C would be at 44, right? So thereafter it's capturing. So when we said the pattern that we're looking for is such that it is not preceded or succeeded by a word boundary, then we got these as output. Because categories, it was preceded by a word boundary. So was the word catalyst. It was again preceded by a word boundary. So it kind of gave us a filter. Let's say we have another text, which is something like this. 200 out of 450 employees of XYZ Inc. signed up for a 60-minute exercise routine, which involves walking 10,000 steps a day. Now, let's say you're only interested in the numbers here. So for numbers, we do a \D. So let's say the pattern that we're looking for is a \D. And let's see if we are able to catch all the numbers. So it's able to identify the occurrence of digits at a character level. So it's saying 200, then it's saying 450, then it's saying 60, 60, then it's saying 10, and 000. So it's able to identify all the numbers. But so let's say we don't want to see it like these broken digits. We want to see it like a proper sequence. So what can we do? Can we surround it with the word boundaries and say digits which have 1 or more occurrences? So D plus means digits repeated once or more. And we're putting it in a way that's beginning and ending with a word boundary. Let's see what do we get now. So first few numbers have been identified properly. 200 is proper, 450 is proper, 60 is proper. But look at this, you had 10,000 written with a comma. So it identified 10. Then it considered comma to be not a digit, of course, and it kind of broke that sequence there and then again picked up 000. So it's not able to get the last pattern properly. What if we make it an option? A lot of times when people write numbers, they may put commas to indicate hundreds of thousands and things or tens of thousands. Let's do it like this. So we are saying it begins with a digit one or more times repeated. And this comma with a question mark is being made optional. Either it's there or it's not. Then we are saying it again is followed by a digit with one or more occurrences and ending with a word boundary. Let's see what we get now. So if you see, now we are able to identify the digits properly because we made the comma thing optional. It may or may not be present. So for these cases like 200 and 450, there was no comma that we had. Of course, we found the entire pattern here itself. And for this case, it kind of found a comma, but then again, look for the digits after that. And wherever there was a word boundary, it kind of ended. Next is this uppercase S, and it's again preceded by a backslash. So we are saying this is a non-white space character. So the lowercase s represents the white spaces, which could be tabs, which could be new line, which could be just the white spaces. Uppercase S is a non-white space character. We are saying one or more occurrences of it followed by a word boundary. Let's see what we get here. So it kind of gets everything that we had in our sentence because we got everything other than the spaces. So 200 out of 450 employees of XYZ Inc. signed up for it. It kind of gives us everything. Doesn't really consider the spaces that we had in between. What if we say we want to look for the spaces followed by the word characters? So this backslash W means it could be lower or uppercase alphabets or numbers or even an underscore. And we are talking about one or more occurrences of this. So what would it return? It is something that's going to be starting with a space, something that succeeds a space, and it's a word character. Contains repetitions of word characters. So if you can see, it kind of everywhere has an extra space in the beginning, and then it's able to identify these patterns, which are word characters only. Let's say we look for another pattern where we say a non-space character followed by a space and again a non-space character. And this plus sign indicates that this non-space character could be repeated once or more. At least has to be once, could be more. Let's say when we look for this pattern in the string, what do we get? So look at this. It's able to identify the occurrence of non-space characters. Let's say in this case 200, then it gives a space, and then takes the other sequence, which again is a collection of non-space characters. Notice it's not doing an overlap. What I mean by that is, if you look at the string, it's saying 200 out, but it's not capturing out of. Why? Because regular expressions do not do overlap. It'll take it with an exclusion. 200 out, then it'll count it from off 450. Then it'll take employees of XYZ Inc. It is not going to do 200 out and out of and off 450, 450 employees. That's not how it works. It's non-overlapping. So that's an important point. You may see that's the kind of output that we're getting here. Now, the last piece here would be to check for specific patterns in the email addresses. And let's say we have a set of email addresses represented in a doc string, and you want to find out which of these are valid email addresses. So some of these are valid, like you have the first name, Albert Schwartz at gmail.com, Lisa25 at outlook.co.uk, Jack Quintana 12 at yahoo.com, but you say Norman @gmail. This is not a valid email address because you don't have the top level domain here. no_email.com, again, is not valid because you don't have the @ symbol here. And Michael Perio at insight.ai could be a valid pattern because we are allowing the use of underscores and dots typically in the email addresses, first name dot last name or first name underscore last name at the name of the domain and .ai. So let's see how we actually go about searching this. So we are saying it could begin with a word character. It could have a dot, underscore, a plus symbol, or a hyphen. So we are allowing a plus symbol also in an email address. If you don't think that's allowed, you can always remove this. Otherwise, we are allowing a dot, underscore, plus, and hyphen here. And then we are talking about one or more occurrences of such patterns. And then we are saying @. So this is the @ symbol. And then again, we have a set which may contain a word character, dot, or hyphen, and it could have one or more occurrences, followed by a dot. Again, we are saying that we may have alphabets, lowercase or uppercase, 2 or more occurrences. When we just put the lower value and don't put the upper value, it may be any number of repetitions of alphabets. And then there's a group that we are using. So sometime back we discussed about the group. So how is this important? Let's see. It's making the subdomain kind of optional for us. So for example, for addresses like .co.uk, now you may have just .com, you may not have .co.uk, but If it is there, we should be able to recognize this is a valid email address. And we are keeping this optional. Why? Because we are putting this under a group symbol and then putting a question mark after this, which means this entire piece is optional. What could it contain? It could contain alphabets with 2 or more occurrences. And then it would end with a word boundary. Let's run this. What are the valid email addresses? So it says albertschwartz@gmail.com is a valid email address. Lisa25@outlook.co.uk is a valid email address. Jack Quintana@yahoo.com is a valid email address. And Michael Barrio@insight.ai is a valid email address. Why did this address not get captured here? It had the beginning, which is compliant, @ which is compliant. Whatever followed after @ was compliant up to this extent. But it did not contain a dot and something followed by it. So it, of course, got discarded. And why did this get discarded? It became non-compliant without using @ in the first place. So we didn't really catch it as a bug. So again, like I said, this is a matter of practice. You may have unlimited options to search for, but this comes very handy when we start working on a data that's really messed up. This was a quick example covering some of the pieces that we discussed on the slides.